So let me begin by introducing myself. Thank you. I will watch for cues. I'm Steve Cummer, professor of electrical and computer engineering at Duke University in the US. I got my PhD in electrical engineering in a long time ago, 1997, from Stanford, which is where I did my undergraduate degree too. And within EE, I was very much on the boundary between EE and applied physics, and really deep down just liked electromagnetics and wave propagation. And the group that I got affiliated with during my PhD time was very much in the applied E&M space and focused on lightning and its effects, in part because that was a time when a lot of new things were being discovered, and it was tremendously exciting to be part of this community. Was doing research where things were being observed, measured, recorded that nobody had known even happened, and in the beginning nobody had a clue as to what was going on. Now we have clues, and I'm going to summarize that 26 years of history for you with a number of phenomena today, with lots of twists and turns and some dead ends that lasted for a decade. Just kind of interesting stories, I think. And since I was guessing that very few of you here do work related to high voltage or sparks or streamer propagation, that you might not be lightning experts, so I have lots and lots and lots of movies. Some of which I think are pretty incredible. So logistically, when you have a question, I have a microphone, but it's not always that easy to pass it. So just shout out when you have a question, and I'll try and repeat it to get it onto the recording. If I don't repeat it, please remind me to repeat it so it gets on the recording. So I've kind of got 4 pieces to this talk. The 2-hour talk is not a standard unit for an academic presentation. I can do 20, 30-minute presentations, done a million of those. Seminars, plenaries, 50 minutes. I haven't done as many of those, but I've done a number of those, and I know what it takes to make a 50-minute talk. I have way less idea what it takes to make an engaging 2-hour presentation. So I may have too many slides here. I just didn't, the nightmare running out of material when there's a lot of time left. So we'll see how it goes, but yeah, we'll see how it goes. Perfect. And now I bet everybody's here. So pictures of lightning. Man, there are a lot of great amateur lightning photographers out there in the world taking some pretty amazing pictures. I grew up in California, which, like the Netherlands, does not have very much lightning. I probably heard thunder growing up maybe once a year. Maybe similar for you all. On that order, probably less than 10. Like, just thunderstorms are not a major concern for you. Now being in the southeastern part of the U.S., the story with lightning is entirely different, and there's quite a lot of lightning there. It's not like Florida, where there's just lightning all the time. But lightning does a lot of things. It strikes the top of buildings with great regularity. It hits every commercial aircraft, apparently, on the order of once per year. Like, every airplane is struck by lightning once a year. Thankfully, that's not really a cause for concern. It doesn't normally cause damage to aircraft because of the conducting skin. And right, if you park yourself in the right place and do a time exposure, you can make epically amazing photographs. This one I like to include up here because here's the thunderstorm. It's a little bit hard to see. There's trees down here. So this bolt of lightning is coming out of the front of a thunderstorm, and that has a specific name for people in the business called a bolt from the blue. And that's the one that tends to kill golfers in the United States, because they maybe hear thunder because this storm can be like 10 kilometers away, but they look straight up and they're like, nope, there's nothing, no thunderstorm overhead. I'm good. But lightning really can do this, and this distance can be extraordinary. So, you know, that rule of thumb, in at least lightning safety in the United States, like if you hear thunder, it's probably a good idea to get undercover some conducting object. Your car you'll pretty safe in there too. But if you hear thunder, don't stay outside. Don't go near a tree. And when I say lightning is everywhere, it definitely is everywhere. You guys have probably seen volcanic lightning photos. Yes, I mean, they're just absolutely amazing. I have a feeling this is a guy who won a National Geographic travel photography contest in 2017. I have a feeling there's a little bit of enhancement going on in that one. But it's still an amazing photograph. From a practical standpoint, you know, volcanic lightning is not really a major concern for you because there are other things you have to worry about if you're standing right there than lightning hitting you. But I do know, for instance, the Tonga eruption in the South Pacific, which was, I guess, about a year ago, there was so much continuous lightning from that eruption at its peak that the lightning detection networks that cover that region completely saturated in their ability to count lightning flashes because it was so frequent. And we'll talk a little bit about why volcanoes produce lightning. It's not really a great surprise once you know why thunderstorms produce lightning. And when I say lightning is everywhere, it really is everywhere. This is a phenomenon that I'm not going to talk in detail about, but it's not very common, but there are a decent number of recorded videos and captured images of it. This is the very first video recording of this particular phenomenon from the early 2000s. It was recorded with an image intensifier, you can tell by the green tint here, by a colleague of mine who's now a professor at Penn State University in the US. And he was on a field campaign in Puerto Rico to capture videos of some of the other things we're going to talk about, hoping that he would get some. His name is Victor Pasco. And he and another colleague, Mark Stanley, were out there for 2 or 3 weeks setting up their cameras, pointing them over distant thunderstorms to try and capture something. And I'm pretty sure that they got completely nothing except for the last night when they happened to capture this. And I think I've got this on a loop. So it's down there at the bottom. There's a thunderstorm maybe 200, 300 kilometers away that's actually below the horizon. And this is real-time video, so this is something that lasts for about a second. There is an audio track recorded to this where they say to themselves, as it happened, because it was visible with the naked eye, lots of words sort of excitement not repeatable in public. And Victor is just saying to himself, my God, it's blue. It was blue. This is something called a gigantic jet. And this is a slightly better sequence, slowed down, of video captures of the same phenomenon from Florida in one thunderstorm from a regular speed video camera. And you can see, I think these are slowed down, I don't know, by a factor of 5 or 10. And for all the world, they kind of look like lightning strokes that are going up out of the cloud, and they just keep going, and they keep going, and they keep going until they run into the conducting ionosphere at an altitude of about 80 kilometers. I think there's a really big one at the end of this sequence. Yeah. And if you're a very dedicated observer, and there are many amateurs who do this, will set up their cameras and just take like 1 second exposures over thunderstorms for an entire night hoping to capture something interesting happening up there. You can see, it's a little bit hard with the light there. This one, blue at the bottom, definitely gets red at the top like this one. This was somebody who just happened, it's not associated with the airplane wing, it just happens to look like that. Flying over somewhere in Southeast Asia, just outside the airplane, taking pictures of the thunderstorm. And this down here, the bottom, you can see it comes right out of the top of the thunderstorm. And up here is 80, 90 kilometers. So this thing is about 70 kilometers tall. And it's pretty epic. And in fact, we now understand, but I'm not going to go into detail about this, that they really are just lightning discharges that start in the cloud. And because wind or turbulence has perturbed what's normally an electric charge layer at the top, this lightning channel is just able to punch out of the top of a thunderstorm and keep going and keep going and keep going until it runs into something conductive. And so it is basically a lightning discharge to the conductor at the edge of space instead of the conductor that is the ground on this planet. This one is hard to see. Definitely not common. Pretty much tropical. Almost all of these have been seen like below 23 degrees latitude. Something about the thunderstorms being taller and windier tends to produce these. Okay, how about some lightning videos? Okay, right answer. You've seen lightning naked eye, of course. It gets a lot more interesting when it's recorded with a high-speed video camera. This was a recording that was made actually by my group back in 2005. You can see here when we were running a high-speed video camera for a campaign, an observational campaign in Colorado. During the night, we would point over distant thunderstorms. During the day, when there was nothing else to do, we would point at close thunderstorms. And this is a lightning discharge that hits ground maybe 20 kilometers or so away from us. And this is recorded at about, I think, 7,000 frames per second. So a lot faster than regular speed video. But you can also see there's a lot happening at timescales that are even faster than what's captured by this. Another high-speed lightning video, and this is one of my favorites. This is recorded by Tom Warner, as you can see there. He is a super interesting guy. He was a B-1 pilot in the Air Force, one of the bombers that carries nuclear weapons routinely around and is stationed for, ready in case bad things happen. But really avid lightning observer. And due to his family circumstances, he has access to a lot of resources. And he, after retirement, just equipped his car with multiple high-speed cameras and would drive around South Dakota and North Dakota, which is the upper Midwest of the United States, stationing and parking in spots and recording amazing high-speed lightning video. And this is one where he's pointing specifically at some tall towers that get involved with this lightning flash. So you can see the channels coming out of the cloud. There's the ground contact. But then there's channels going up from this distant tower back into the cloud. Fun fact, and then lots of individual dart leaders, lightning flashes that are coming back down and reconnecting to that conducting channel that's attached to that tower. So you notice there that like the attachment to the tower was not from something coming down and connecting to the tower. It was actually a lightning flash that hit the ground somewhere else, and then the tower sent up a lightning channel that made its way back into the cloud. That's actually sort of the more common way that towers get involved with lightning flashes. And it just keeps, oh, no, we're looping. So, pretty amazing video. But I want to plant the seed here that as much as you can see optically below the thundercloud, there's obviously a lot happening inside the thundercloud that you can't see optically. But there are ways to see it, and that's going to be like the second to last piece I'll talk about, because it has a Netherlands connection. Oh, and yeah, that's a cool still image from another guy who's probably the best in the business right now at recording high-speed lightning video, a guy named Marcelo Saba. He's a professor in Sao Paulo, Brazil, and has access to some good cameras and talented students and lots of lightning in Brazil. I will say a little bit more about this one at the very end, because it's quite interesting. Actually, I can pose a question right now. Obviously, there are lightning channels coming out of the cloud about to do something. There are lots of upward channels coming from something attached to buildings. These ones sure look like they're actually attached to like metal towers or antennas, or maybe lightning protection, like lightning rods. This one here looks like it might actually be coming off the building itself and not off of lightning protection. This one is coming off the building itself. This one is coming off a lightning rod. No need to answer it now, but just plant the question in the back of your mind. Which one of these is going to attach and complete that lightning stroke? It's very hard to tell from this still image. And if I were forced to guess, I would say that one. But it's not that one. Okay, so to the first phenomenon that I want to talk about and actually get to a little bit of physics here. And this goes back to those, mid-90s where people were just discovering a ton of things that are associated with lightning and driven by lightning that we had no idea were there, really. And in retrospect, it seems both the physics seems obvious, I think. I'm going to try to convince you of that. And it seems like we should have been able to figure out that these things were there before the 1990s. But a lot of it has to do with technology. Like, it's very easy now to buy a super cheap surveillance camera that has pretty good resolution and very good low light sensitivity. And it just wasn't easy to do that back in the 90s. But this is the kind of thing that now people do routinely, and for $500, you can buy a good camera and connect it to a computer and run it with software. One called UFO Capture is one that I've used before, and it's still out there, that just takes the video feed, and you can define areas in the image that it will watch for changes. And when there's a change in that area, it will record a certain length of video per your specifications. And so you can just set up a camera anywhere you'd like, point it somewhere. This one happens to be at the edge of a large, maybe 3 hectares or so, empty field close to Duke University where I have some of my equipment set up. And you just point that camera all day, all night, have it trigger on whatever interesting things happen, and ask, what do you capture? Well, lightning, for sure. That's an easy one. There's plenty of lightning near my part of the United States. Sometimes those flashes get close, not always. What else do you capture? You get a decent number of meteors at night. No huge surprise there. Some are pretty big. That one must have been really bright because that's the full moon, like sort of burning a hole in the camera. There's a lot of wildlife that shows up in different ways. That was probably our best capture of those, but we would have deer running around. For like a year, there were bats routinely at dusk that would just show up en masse, sweeping across the image, and then they went away. I don't quite know what happened. But for sure, if you do this pretty much anywhere in the world there is lightning, you also see that, which is not like the most amazing video, but that's definitely not lightning. It's pretty high in the sky. It's not so easy to tell how far away it is and so how big it is. If you watch that sequence, you could notice that there were background flashes around the same time as those streaks in the sky. So it sort of seemed like these were maybe connected to distant lightning. And the reality is that nobody really knew these existed until 1990, which I guess it doesn't say, but this is what science papers looked like long, long before your time. This was published in Science in 1990. This was the very first sort of scientific documented image of this happening above a thunderstorm. And this was recorded, Jack Winkler and his group at the University of Minnesota, and what they were doing was testing a low-light video camera to image the aurora and record it. That was their main purpose. And they wanted to point at a reasonably low brightness light source that was transient. And so they pointed over a distant thunderstorm like 500 kilometers away where you could sort of see scattered light in the atmosphere, but it wasn't very bright. And they got that. Interestingly, there was a paper a year before that that was not not as widely read because it wasn't in a top journal, that went through a history of reports by airline pilots and all the interesting things that they saw above thunderstorms, a lot of times out of the corner of their eye. And not surprisingly, those guys did not like to report that they were seeing strange flashes out of the side of their vision over thunderstorms because people who organize airline pilots don't like to hear that sort of thing. So if you ask them off the record, they would say yes. And again, it was totally by accident that it was documented. Oh, here's a fun fact. Do any of you know of the American author Kurt Vonnegut? That is his brother, Bernie Vonnegut, who was a lightning scientist for a long time. And actually, Bernie Vonnegut was one of the people in the 50s who was super involved with cloud seeding by silver nitrate to try and drop stuff in clouds to induce rain. He was deeply involved in that work, but also in lightning work. Anyways, this is what they look like with them. Oh, yes. Ice 9. Sorry, the question was related to Cat's Cradle and Ice 9. Oh, yeah, you know what? Actually, I think I did read that Kurt Vonnegut kind of got the idea for Cat's Cradle and Ice 9 related to his brother's thunderstorm research and dumping strange particles into clouds. So yes, directly connected. Thank you for asking that question. I think that's true. So this was recorded by, I won't call Harold Edens an amateur. He's a professional lightning guy, but also super interested in photography. Recorded in New Mexico with just a regular DSLR camera that he would point over thunderstorms and have it on 1 second exposures repeating all night long, and most of the time you get nothing, and when things are good, that's what you get. You used to have to modify these cameras by taking out the infrared filter to increase the sensitivity, which led to images that were great but were not really true color. But camera sensors are now sensitive enough that people don't have to make that modification for this kind of thing. And so this is a pretty true color image, and these things really are like blood red at the top. I've never seen one with the naked eye, but I am told by people who've been in this business for a while, when observations are good and you're looking over a thunderstorm that's really active and your eyes are really dark adjusted, that you can see these. They're very brief flashes. In regular speed video, they only show up in 1 frame, so they're like significantly shorter duration than 33 milliseconds. So if you don't know what you're looking for, you're just like, what the heck was that? Because it's just like 1 frame in your brain. But they are huge. This one is 200, 300 kilometers away, and the volume of space that they're filling is about a 50 kilometer by 50 kilometer by 50 kilometer cube. So they are pretty spectacular, and they're just not uncommon. I mean, if you set up over a thunderstorm almost anywhere in the world, and maybe record over 10 of them, you will probably get a handful at least. A second image from another amateur photographer, I think that one's a little bit better. And yeah, they're pretty amazing. Oh, these things are called sprites. Not my favorite name, but it was come up with back in the early 90s, when people were starting to document these. And the guy who came up with that name, Dave Sentman at the University of Alaska, he wanted to come up with a name that did not ascribe any particular physics to it, because we really didn't know the physics back in the early days. I mean, from that picture, it kind of looks like it's something going up, and who knows what it is. Of course, you look at that and you know that that's just a whole lot of streamers. But sprites is the name. Okay, and what makes them? Seems like strong electric fields from something or somewhere is probably responsible. But I guess above the thunderstorm somehow, not like in the thunderstorm. So taking an even step back from that, like, how do thunderstorms even work? Obviously, they are electrically charged, and charge is separated on a large scale in order to make that work. So, question number 1. How does charge even get separated in thunderstorms at very small spatial scales? But what would create that electric field in the first place? For sure, but the question here is like, how do you get that 30 kilovolts in the middle of the thunderstorm in the first place? Somehow charge has to be separated. That's a great guess. The real answer is even more boring than you could possibly imagine. It is triboelectricity, which is the fancy word for charge separation when you rub stuff together. That's maybe the answer to my second question. So the first question is like, where does charge even like become separable? And what you have in a thunderstorm is hydrometeors, which is a fancy word for water particles, ice particles, kind of half frozen, half not frozen particles called graupel. And those are all a little bit different and appear in sort of different layers. And when a water droplet and ice collide, they exchange a little bit of charge. Same way dust particles do, and that's what ultimately drives lightning and volcanoes. Same thing. It's little particles colliding to create something that's positive and something that's negative after colliding. But then number two is, okay, now you've created a whole bunch of slightly charged particles that are all basically in the same space. How do you get the positive charges dominantly in one place and the negative charges in another place? I don't. I'll ask you afterwards, but that, not surprisingly, that's not the answer. Because you've got a bunch of positively charged ice particles, negatively charged water droplets that are wanting gently to recombine, because positive and negative. Yeah. Okay. Right, the water falls down, and if populations of, say, water and ice are preferentially charged, then charge is being just one flavor, one sign of charge is being rained out of the cloud. That is a good point, and that is definitely part of it. Yes, stratification by wind. Blowing the lighter particles up and less effective at blowing the heavier particles up. And so if the light particles are charged preferentially one way, then you get that charge at the top of a thunderstorm and what's left behind, the opposite charge at the bottom of the thunderstorm. Correct. Or maybe rain. These two things definitely both matter. But wind is an essential component. Yep, you need the friction of things colliding, which is probably aided by wind, just making sure things are turbulent and colliding. And then wind, generally like strong updrafts in the middle of a thunderstorm. And that means the stronger the winds are in a thunderstorm, the stronger the electrification typically is. The complexity of how this triboelectric charging occurs is astonishing. People have built cloud chambers to try and measure this and control humidity and temperature and collide particles and measure these things, and none of those experiments ever delivers a consistent answer other than there's always charge separation. But how it occurs preferentially, I think it depends really in a complicated way on the surface physics of these water particles or ice particles, which is really complicated. So we're not going to go down that rabbit hole. But hydrometeor collisions on the small scale, and then something like wind plus rain on the large scale. And so before a lightning flash, when a thunderstorm is charging up, it often looks like this. Positive charge at the top, a big negative charge towards the bottom, and then maybe a little bit of positive charge also at the bottom, which I haven't said why, and I'm not really entirely sure why that appears there, but people know this by sending balloons up through thunderstorms with two big electrodes and just measuring the electric field, and from that inferring the charge distribution. And this is what it often turns out to be. I should emphasize, we're probing the question of what is it that makes a sprite happen at all. So one more piece of the puzzle, because that's not quite it, because the air is a conductor. It's not a very good electric conductor, but it's not zero. And the higher you go, the higher the conductivity is. And so this distribution of charge is going to leave you with some net electric field up here that, because this positive charge layer is closer, it's going to want to be pulling negative charge down. And how does that happen? Here's the first taste of real physics. Super basic. First, just an electric conductivity profile in the atmosphere. Sorry for that display glitch. That is Mac to Windows. But because of ionizing radiation of various sources, the conductivity increases as you move up in altitude. It starts to get much more complicated, because at above 100 kilometers, that's when you're deeper in the ionosphere, and instead of there just being ionization sources, there's also transport and different input radiation. It starts to do like this, and then it becomes an anisotropic conductivity due to Earth's magnetic field. So that's a question of like ionospheric physics, which we're not going to do very much of today. But it does get quite, here up to maybe 70, 80, it's pretty much like this. And above that, it gets much more complicated. Dielectric relaxation time. Here's the question. Parallel plate capacitor. What's the capacitance? All those pieces are in there. The capacitance is the area, because capacitance goes up with area. Times epsilon naught, permittivity of free space, divided by the separation between the two. How about the resistance of a block of material that's exactly the same geometry between two plates? Well, the resistance, if a conductivity, there's a block of conductivity between two electrodes that have area A and they're separated by D, that resistance is D, the separation, divided by the area, because the more area there is, the lower the resistance, and the more separation, the higher the resistance, and 1 over conductivity. So if you treat that R and C of the same geometry and compute the RC time constant, it is simply epsilon naught over the conductivity. And so if you apply an electric field to a conducting material by, say, putting charge there and then let it go, how long does it take to relax back to an uncharged state? It is that time constant. And as a function of altitude, that's what this looks like. So it's long at low altitudes, but it's a fraction of a millisecond up at 70 or 80 kilometers. And that is super relevant to the question of how sprites initiate. Because before the lightning, that electric charge time scale, it's on the order of seconds, is how long it takes for the electric field to build up inside the thunderstorm. And so any electric field that's created up here at these higher altitudes, there's enough conductivity to sort of instantly relax away that electric field. And the charge will simply leave that area and move down. But once you get to below about 20 kilometers, that dielectric relaxation time becomes very long. And so you have one more charge layer that appears at the top of a thunderstorm that's called the screening layer, that just shows up there because as this charges up, it makes an electric field up here which drives a negative charge to move downward. And so you have just this layer of negative charge that's here in order to reduce the electric field up above. So that's what you've got. And then what happens when there's a lightning stroke that connects one of these thunderstorm charge centers to the ground? And let's just say it was that upper positive one. Well, all of a sudden, in a very short amount of time, less than a millisecond, a fraction of the charge that was here gets dumped to ground, a good conductor, and then just disappears from the system. It goes somewhere else on the surface of the planet. And so this screening layer that was doing a great job of shielding the higher altitudes from any electric field now is not doing that anymore. In fact, it's because the charge distribution has changed down here. Now you have a pretty serious charge imbalance, and there's a transient electric field that occurs above the thunderstorm in response to a lightning flash. And the more charge that gets moved in that lightning stroke between this and ground, the higher the electric field transient is up here. Now, of course, that electric field transient will relax again, and more charge will come back down and make everything disappear. So under what conditions is that interesting enough to maybe do something? Well, the key insight here comes from the trade-off or the balance between the magnitude of that electric field as a function of altitude. And you can think about that as, moving from this system to this system, use superposition. Any chance you get, use superposition if your system's linear. And what we've done is basically parked an additional amount of negative charge there to remove the positive charge. And we've got a ground layer, so we use the method of images. And there's also then a equivalent positive charge here. And so that lightning stroke has added a new electric dipole to the system. And the electric field then will decay as 1 over r cubed as a function of altitude as you move away from that dipole electric field change. So this is all really just electrostatics in Coulomb. But the breakdown electric field, basically the electric field strength that it takes to initiate a spark, decays exponentially with altitude because it is proportional to the density of the air, and that's decaying exponentially. And so at some altitude, if this dipole electric field is big enough, the electric field transient will be larger than that breakdown field because one's cubed, and one's 1 over r cubed, and one's exponential. And exponential always falls faster. And the amazing thing is, the saying I'm reminded every time I go through some of this, if you want a good new idea, go read an old book. Man, those old guys knew some stuff. And this was first described by C.T.R. Wilson back in 1925, who sort of appreciated this interplay between the 1 over r cubed and the exponential. And C.T.R. Wilson won the Nobel Prize for what? Physics people here? Anyone? No? I didn't. I mean, I wouldn't have known had I not worked in this space. He's the guy who invented the cloud chamber for particle physics tracking, like visualizing that. Although, kind of like Isaac Newton, whose first love was alchemy, and he really just did physics and math because he was better than anybody else at it, but really just wanted to be left alone to do alchemy. C.T.R. Wilson was really into meteorology, and that's what he spent most of his time thinking about, but happened to invent the cloud chamber along the way, which revolutionized particle physics. And so what happens is if you have this electric field transient big enough, you can exceed that sparking limit and drive electric breakdown at high altitudes. And it always starts at high altitudes. And it turns out that what it takes is about 100 coulombs of charge removed suddenly from the cloud, which is a lot of charge, but it's actually not unheard of in lightning. And you remove it from an altitude of about 10 kilometers, which is sort of typical for a thunderstorm, and you compute the electric field, and you find that around 70 kilometers is where you suddenly have this transient electric field that is high enough to spontaneously create a spark or a streamer. And it's a really straightforward problem to analyze, either analytically. This is probably the best paper back from 1976 that really looked in detail at this problem. They didn't appreciate the breakdown aspect of it. Or you can simulate it numerically, which is what my good friend Victor Pascoe did, who really illuminated all of this theory, just with an iterative solution of Poisson's equation. So you've got electric charge, you can solve for potential, then from potential you got electric field, and then from electric field and conductivity you've got current, and then conservation of charge gives you how the charge rearranges due to that current. Take a short time step, iterate over and over and over again, and you basically produce that solution that I sketched out there. Yeah, and so it was, remember the discovery was 1990. 1995 was the first paper that started to poke at this, and then 1997 is the more complete picture from those papers from Pascoe, understanding what happens. And everything became very clear once we got high-speed video of sprites. This is the camera setup for that 2005 campaign that I was involved in Colorado. A friend and colleague named Walt Lyons, who was a meteorologist by training and actually was a TV meteorologist before that, did mostly expert witness kinds of work afterwards. He set up this giant observatory in Colorado that looks out over Midwestern thunderstorms, because he loved to do this, and would just invite everybody to come hang out at his place in the summer for as long as you wanted near Fort Collins. Bring your camera, he'll set it up to this platform. It's like remotely pointable. There are a bunch of photometers here too. This is my high-speed camera that we rented, photometer array. It was a great time. And I had a French engineer in my group at the time, and he was the guy who went out for 3 weeks to man the camera and keep it running. And, you know, it's really hard to focus high-speed cameras with an image intensifier on them when there's like no object there. And we really wrestled with that for the first 2 weeks of the campaign and recorded a lot of sprites, but like none of them were like fantastic. And then literally the last night of the campaign, angels smiled upon us, and that's what they look like at 5,000 frames per second. He sent me that by email. I got it like on a Saturday morning. I was in my office. I was just like, thank you. And since, well, so you can see very much where they start at the top, and most of the motion is down and some subsequent motion up. So that right there is those sparks spontaneously initiating where that electric field gets high enough. This is the very best video of a sprite that I think has ever been recorded. There's a retired Air Force colonel who's a professor at the U.S. Air Force Academy who continues to do this, and he's very good at what he does. And this is a video that you can see I didn't have it, so I ripped it off his Facebook page. So this is like a screen recording of his Facebook, so that's why that's me trying to start the video. But watch this. So this is zoomed in on like a fraction of that whole thing. And all those little dots are these streamer tips. And the complexity is huge. Like they start down, but then they go up, and then they go down again, and there's overlapping, and they're obviously influencing each other. So there's charge left behind, controlling the electric field. You'll notice that these sprites are dots, whereas mine were streaks. The reason for that is the US military and its needs. And image intensifier technology. The US military will basically buy up any and all image intensifiers that are manufactured. And the image intensifiers with the highest quantum efficiency, because what they are is basically electron multipliers, and then there's a phosphor at the end to convert those electrons into light that's seen. The highest quantum efficiency phosphors are ones that have a persistence, so they phosphoresce for a handful of milliseconds. So that makes all of this sub-millisecond dynamics very streaky, and it appears as blurred because of that phosphor decay time. Jeff is lucky enough, probably partly due to his ex-military connections. He has image intensifiers with very special phosphors that have a much shorter phosphorescence lifetime. And so that decay time means he can actually image what sprites really look like, which is just these streamer tip dots moving back and forth. Although I saw him at a conference in Chicago in December, and he is super bummed because FedEx lost one of his special image intensifiers that are very difficult to get again. But he still has one, so don't feel too bad for him. Here's my one nod to this notion of streamers. Like, this is a totally fundamental electric breakdown piece of how that goes. At least one student here. Two? Okay, two of you. Study that. Right? Yep, exactly. You close your eyes at night and you see streamers. Are you guys on the simulation side? Of course, because... Okay. But not the experimental stuff. This is sort of how breakdown occurs, and this is a laboratory image. You can't see this. This is 80 centimeters. And obviously this is 40 kilometers. Everything just scales with air pressure. So at STP or close to STP, like streamers are millimeters in size, and up at 60 kilometers altitude, they are kilometers and hundreds of meters in size. But it's same fundamental physics that's super complicated because there's so many different ionization sources at play. There's photoionization, there's electric fields, everything is nonlinear. The chemistry plays a role, what gas this is happening in. Streamers look totally different. It's complicated stuff, right? And there are some interesting questions here because we understand the basic physics of how sprites start, but like initiating a streamer without an electrode, like a sharp conductor that you're applying a really high electric field to, is not so easy. So somehow that is happening in the mesosphere at 60 or 70 kilometers. All that complexity that you saw in Jeff McHarg's video about what these sprites are doing, how there's initiating down and then up and then down and interacting. And, you know, you saw there's thousands of streamers in the real thing. I think maybe tens of streamers is what can be simulated at best right now, like very state of the art. So we're nowhere near to be able to actually simulate or even compute all of that complicated dynamics. But yep. No. Let me answer, and you tell me if I'm right or wrong. The disparate scale sizes involved in the problem. because the individual streamers themselves have to be modeled like at a resolution that is smaller than those streamer tips. But when they fill such a huge volume, it's too many orders of magnitude difference between the full space that you want to simulate and the grid size you need to capture those internal details. Fair statement?
And then when you have several streamers, it becomes a three-dimensional problem. So the number of grid cells that you need for that also increases by another order. So you need like a ludicrous amount.
Right, to solve the 3D problem, like 10 to the 6 cubed, or I mean, just it's becomes intractable very quickly. So, sorry? Oh, why? That's a good question. It all has to do with what species is being excited and is easiest to emit photons. And this is not my expertise, but it is N2 first positive. Does that mean? So it's a nitrogen emission. Is it maybe it's ionized nitrogen molecule? Because almost everything is in sufficient numbers at those altitudes to be ionized. They do turn blue below about 40 kilometers. Yeah, question.
Microphysics that fall off, or that are smaller than your cell size, and something like that just doesn't exist right now. I don't know the details about this turbulence modeling, but I guess you introduce some kind of viscosity or something, or some diffusion, and say all these processes are roughly diffusing.
So for the recording, I feel like I have to say something. The question was about turbulence modeling, which is another field where I don't know that much about, but I know it's disparate spatial scales, that turbulence has to be captured on really small spatial scales, but then to be interesting or useful, you have to be able to simulate much larger volumes, and how to handle that, and whether techniques from turbulence can be adapted to streamers, which is an open question. But for sure, there are a lot of nonlinear systems like this just have that feature, that really small scales are important, that you need to capture in simulations. But for relevant problems, you also need a really big volume. And it's challenging no matter how you slice it. Okay. Something different. This one involves antimatter. I think I promised that in the abstract. This is the one that kind of still blows me away. So this, you can tell, is not real. It's an animation. So if you could see this next phenomenon from a viewpoint like this, it would kind of look like that, where NASA, when they create animations like this, apparently, gamma rays are always magenta, electrons are always yellow, and green, you can see a few of those are always positrons. Like there's NASA's gamma high energy astronomy videos must always follow this color scheme. And so that's pretty spectacular. A bunch of gamma rays and electrons and positrons. The charged particles are following magnetic field lines, but the gamma rays can go anywhere they want to. Apparently coming out of a thunderstorm. The reality, the reason I show this video first is because the reality is the discovery was that. which is not a terribly exciting figure if you don't know what it is. In fact, the label, it says, if you can't read it, it says signal versus time. And this one was in Science too, in 1994. The gamma ray, the Compton Gamma Ray Observatory was a gamma ray astronomy satellite, you know, looking for gamma rays from supernovas, that sort of thing. Had an instrument on it called BATSI, and every once in a while, they would detect completely unexpectedly these short millisecond or time scale bursts of gamma rays that they had enough directional information they could say it was coming up from the Earth, which was like, there was nothing that should be doing that. Obviously not, because they got it in Science, and the only way you get into Science is if you surprise people. They were able, in this paper, to sort of connect that location on the Earth to thunderstorms, which kind of makes sense. It's a pretty energetic thing. And so, how about a little bit of physics here? What might be happening for accelerating electrons in air? This plot shows, as a function of electron energy, so 10 eV up to, well, 1 MeV, 10 up to a GeV. We're not going to be going up there. This is the effective frictional force that an electron feels being accelerated through air. And so here's electric field and versus energy. And the thing to note is that that effective frictional force goes up and then it goes down and has a minimum at 1 MeV. And so if you somehow have an MeV electron in air, it is way easier to accelerate that MeV electron than it is to accelerate a KeV or 10 eV. And I think that's fundamentally due to relativistic aspects of scattering. So that's kind of interesting. So let's sort of step through what this curve means in terms of accelerating electrons. So has anyone ever stood near a high voltage, high tension power line and you hear buzzing? Great, that's this. In air, ionizing molecular nitrogen takes 15 eV of electron energy. And so if we take 15 eV, run it up here, and figure out what electric field is required to accelerate a 15 eV electron in air and keep it going, it's about 3 megavolts per meter. And that is like the sort of standard electric breakdown threshold. That's 30 kV per centimeter, which you sometimes see it as at STP, standard temperature and pressure, 1 atmosphere. That's how much electric field it takes to accelerate an electron and keep it going. And so what'll happen is at that field, if you accelerate an electron from low energies, and it gets up to 15 eV, and then it can ionize more, and then drops down the curve, accelerates up, ionizes again, and so you can get this avalanching process of electrons up to 15 eV. But at 15 eV, that process basically stops because you need to increase the electric field a lot in order to get any more energy out of it. And so that's like the Townsend discharge or the Townsend avalanche, corona streamers. That's what you hear when you are near a high voltage line, is those streamers buzzing. And if there's a lot of current that can be supplied through that, you can sometimes see the glow associated with that. But that's totally low energy stuff. Another interesting point is up here, And this is the electric field, which is really big. So this is about 10 times higher, 30 megavolts per meter. At that point, every electron of any energy will accelerate. So if you can somehow create 10 times larger electric field, every electron will just accelerate and run away and keep ionizing. And that's called cold or thermal runaway. And that's what's responsible for lightning making X-rays, which it does. The challenge is that's a really big electric field. And as soon as you hit that, like electrons start leaving your area of interest. And so that tends to reduce the electric field. So this is a kind of thing that only happens for very short transients because you just can't maintain it. But at high energies, MEV electrons will continue to accelerate at like 10 times lower electric field than that Townsend discharge. And so if you have some MEV particles to begin with and apply this much lower electric field, well, they'll accelerate. They're such high energies that they will ionize everything and leave some additional high energy electrons behind, which can then accelerate and ionize and leave some additional high energy electrons behind that accelerate. And this is the relativistic runaway electron avalanche. So it's an exponentially growing population of MEV electrons creating gamma rays via bremsstrahlung. And this was a mechanism that was first identified back in the 60s and sort of sketched out in more detail in the 90s before the discovery of these terrestrial gamma ray flashes, which I haven't named yet. That's what they are, terrestrial gamma ray flashes. And amazingly, same CTR Wilson actually speculated about this and appreciated something about that frictional force being lower on high energy electrons even back in the 20s, and thought that something like this could occur, but he didn't sketch it out quantitatively. So you start to apply that notion, the relativistic runaway electron avalanche, to this question of how can we make a gamma ray beam that launches itself into space that starts with in low altitudes or anywhere that has at least 10 to the 18 high energy electrons, because that's what it would take to create the gamma ray flux observed by a satellite at like 500 kilometers altitude, which is where these are observed. And you do some calculations, and what you find is that for potential differences on the order of 100 or 200 megavolts, which is what you can find associated with thunderstorms, either above or below, you can get an avalanche multiplication factor on the order of 10 to the 4 or 10 to the 5. And so work backwards, that means you somehow need 10 to the 12, 10 to the 13 high energy electrons at the start to make this thing go, to make something bright enough to be seen on orbit the way it is. And so the big questions were, at the time when these were discovered, where is that electric field providing you the 100 megavolt potential drop? It's associated with thunderstorms, but is it above thunderstorms or is it in the thunderstorm? And where are these 10 to the 13 electrons that start the process coming from? So, human beings are very good at associating things that occur at similar times that may or may not be connected to each other. Sprites were discovered in 1990 and TGFs were discovered in 1994. And the first thinking was, oh, these are the same thing or produced by the same thing. And this electric field that's accelerating these MEV electrons is above the thunderstorm, the same thing producing the sprite. And there we go. And the 10 to the 13 electrons are coming from simultaneous cosmic ray air shower. that is producing this giant seed population in the atmosphere that then runs away up and produces the gamma rays. But you start working on the numbers associated with that, and the size of the lightning flash is like 10 times bigger than anyone has ever seen on planet Earth. How are these cosmic rays there at just the right time when a lightning stroke happens? That's like two simultaneous things that are not connected, that shouldn't be connected. And one huge challenge was that this satellite saw like 70 TGFs, and then there was no other satellite up there that could see them until 2005. So there was like a decade where anybody could come up with any idea, write it down on a piece of paper, and nobody could experimentally say anything about it because there were no new observations being made. And there were some very strong personalities in the field who were very committed to these ideas of things happening above thunderstorms. And they really, really pushed that idea hard and did not care very much for people suggesting that it might be happening somewhere else. And then in 2005, thankfully, another satellite got up there that could detect TGFs. It was a solar X-ray satellite, but we knew about TGF, so we could design, that satellite was designed to be able to not trigger on orbit, but actually bring down to Earth telemetry, via telemetry, all the gamma rays and X-rays that were observed, like time tagged, so that instead of relying on an on-orbit trigger to hopefully capture these things, all the data was sent back down and we could search, not me, but others could search that data at their leisure for these terrestrial gamma ray flashes. And that changed things a lot. And we realized that there were at least 10 times, maybe even 100 times more TGFs than the original measurements had suggested. And we very quickly realized that the lightning that is associated with TGFs is way too small, doesn't even make a sprite. It's like modest at best. So there's no way that these things were happening at high altitudes. And also another thread on the same idea is some detailed simulations of the spectrum of gamma rays that was making it to on orbit also convincingly showed that it had to travel through a lot of atmosphere to get there, and so was not happening at high altitudes. So these are low altitude, inside thunderstorm phenomena. Okay, we can live with that because 100 megavolts is feasible of total potential drop, feasible in a thunderstorm. But how do we get that 10 to the 13 electrons back at the source? And the leading idea for this emerged in 2003 from my good friend Joe Dwyer, who I believe came up with this just by doing Monte Carlo simulations of how these MEV electrons should behave and just accounting for all the cross sections and what they could possibly be doing as they travel through air. And what he first was the first to realize is that these are, in this figure, they're running away downward. That all you need is one electron and it will avalanche and you get maybe 10 to the 5, which is nowhere near enough. But within that, these gamma rays are high enough energy that they can create an electron-positron pair because it's above 511 keV. And so you get some positrons, and they move backwards in the electric field region and go back to the start where they collide with stuff and create new seed particles that then run away forward and then feed back. And so electrons forward, a few positrons back, electrons forward, a few positrons back, and very quickly that amplification that comes from all of these positrons running backward in the field means that you can get this 10 to the 13 spontaneously from just one MeV electron in the beginning. And there's always one MeV electron around where you need it from cosmic rays. There's not always 10 to the 13. And so to everyone's best guess, it does seem like antimatter in thunderstorms is playing a key role in this process that happens basically everywhere on the planet. It's not very common, but it occurs everywhere on the globe, as shown on that map, where there's a lot of lightning. Not a lot in Northern Europe here. Thunderstorms are just not strong enough. Maybe it's a question of total potential drop. Nobody's completely sure why they're so equatorial, but it does need a vigorous thunderstorm and a lot of wind and a lot of charge separation to create a big enough potential drop. And a little bit more insight into what lightning process is happening at the time. If I had time, I would do a lot more background on this because these radio measurements of lightning are my real bread and butter. But there's just not enough time to do that. So lightning's a powerful radio emitter, especially at frequencies that match the time scale of currents flowing in lightning, which often is around tens of microseconds. And so invert that, tens to hundreds of kilohertz is where lightning is a very powerful radio emitter. Nobody ever listens to AM radio, of course, but ask your parents or probably your grandparents who did listen to AM radio, and they would tell you that if there was a thunderstorm nearby, you hear all this crackling going on. That's radio emissions from lightning itself. And so my group, we do a lot of radio recordings with sensors around the world, and with GPS timing, we can connect specific radio emission sequences with terrestrial gamma ray flashes to get some insight into what's happening. And here's an example of one where you just see a sequence of pulses and a TGF happening in the middle of that sequence of pulses. This is, if you stare at enough of these, you'll know that this is the kind of sequence that you see at the very beginning of a lightning flash when a lightning leader starts to move upwards. And if you zoom in a little bit more on these individual pulses, those of you who are close, you can kind of see every pulse. There's the big one, and then there's two little blips afterwards. Big one, two little blips. Big one, two little blips. If you zoom in, you can see that even more clearly. Does anybody know why there's reflection 1 and reflection 2, and what I'm even talking about when I label those reflection 1 and reflection 2? If it helps, this signal is recorded a few hundred kilometers away from the lightning. And this big signal is the thing that's directly radiated from the lightning. Yes, it hits the ionosphere and comes back down. These frequencies are strongly reflected by the ionosphere. But, okay, follow-up since you're on it. Why are there two reflections? You read ahead, didn't you? Okay, you're very clever. This happens when the source is above the ground, and one pulse goes straight to the ionosphere and down. One bounces off the ground first, then ionosphere, then down. And those are slightly different path lengths, and so there's a small time difference between those two that's on the order of tens of microseconds. It's not much, but you can see it. And if you really look closely, if you go up to here, you'll see that these two pulses are farther apart than these two pulses. Trust me, they are. And what that means is that these sources are moving up in altitude, because the higher the altitude is, the longer the path difference is between those straight to ionosphere down and ground bounce up and down. And so even though we were pretty far away, right, you figured that out. Awesome. What's happening in the thundercloud, this sequence of pulses is starting at 9 kilometers, which is a very typical lightning initiation altitude, for sort of low latitude thunderstorm. Thunderstorms in the Netherlands are way lower altitude, but this is like tropical. And there's a lightning leader that is propagating upwards steadily about 5 kilometers total to 14 kilometers. And where the TGF occurs is right in the middle of that sequence. And so the thinking is that you're in a thunderstorm, you have a background electric field between two charge layers that is close to the threshold to be able to trigger this relativistic runaway electron avalanche, but not above it. And now a lightning leader starts to propagate up, which is a conducting wire, essentially, carrying the potential of down here up in altitude closer to the positive charge layer. And so the total potential drop across the entire thunderstorm gets squeezed into a smaller amount of space above the lightning leader. And so total potential drop over a shorter distance means the electric field has to be higher. And so as the lightning leader moves up, it creates its own electric field that adds to that background field. And the lightning itself gets long enough that it's able to nudge the electric field over that feedback threshold and suddenly create a terrestrial gamma ray flash that emerges from 11 or 12 kilometers altitude. And every once in a while, Mother Nature cooperates and makes pictures even clearer. Here's an easy quiz. Which of these pulses is different than the others? It's really easy. The one with the magenta dots on it. Why is it different? It's longer, right? Like these all have very sharp edges. These are all these lightning leader pulses. And this one, which has a much slower rise time, is actually the one that if you back propagate everything to the thunderstorm is totally coincident with the terrestrial gamma ray flash. And so we think that this is the pulse that is not created by the lightning, but is created by those 10 to the 18 electrons accelerating in this RIA process. And so it's the signature of the TGF. Yeah. How do we, yeah, okay, why? This is one of the frustrating things. The question is, why do only we see this sometimes? What I mean by that is sometimes it's crystal clear like this, and this process, that slow pulse, is overlapping nothing else, and so it's super obvious. There are other times where the lightning leader is doing a lot of other things at the same time, and it's very difficult to see this slow pulse because of all the other junk that the lightning leader is doing, seemingly doing at the same time. And the reality is, and this we don't understand, some terrestrial gamma ray flashes are seemingly produced without a lightning leader like this. They're clearly coming from a thunderstorm, but they're just like poof, out of thin air, which in principle could happen, but it's hard to imagine how the electric field gets big enough, fast enough to trigger this. Because what really should happen if you have slow thunderstorm charging is you'll get close to that electric field threshold and you'll start to accelerate any MEV electrons hanging around, and they will create a whole bunch of ionization that moves in response to the electric field and basically moves to negate the electric field. So anytime you poke up slowly above this threshold, this process should push it back down. And in fact, that does happen because there is a thing called gamma ray glows that you can see if you fly aircraft close to thunderstorms. you see these sustained minutes-long enhancements of background radiation that we are pretty sure are this process happening very slowly and pushing the electric field back down. So, interesting that antimatter in this positron feedback also plays a role in the maximum electric field you can possibly have inside a thunderstorm. And if you try to turn it up slowly, it will push itself down via this process. Again, these are several MeV, so pretty high. Because again, the source is this runaway, which occurs most efficiently for MeV electrons, but you can get higher energy ones as well. So, great question. I do say that. Okay, there's 2 places in the world where these seem to be measurable on the ground. The west coast of Japan and high in the mountains of Armenia. Now, the reason for that is partly because that's where people are trying to make these measurements. There's a cosmic ray observatory high in the mountains of Armenia, and there's been a lot of interest in thunderstorm research on the west coast of Japan because of some very unusual thunderstorms that happen there in the winter from like super cold Siberian air coming over a much warmer Sea of Japan. But the common thread is those places, the thunderstorms are really low altitude. Like in Armenia, they're often in the thunderstorm because they're at like 14,000 feet, 4,000 meters-ish, something like that. And in Japan, the thunderstorms are like 1 kilometer high, like they're super low for some meteorological reason. So you're exactly right. If normal thunderstorms, you can't see this on the ground, which is why people fly high altitude aircraft to try and catch them. But in a few places in the world, if you just set a gamma ray detector out and record all the time, you may see this when thunderstorms come nearby. Just a slow ramp up and decay. And that was my last TGF slide until Friday, when this paper came out, and I have yet to read it in detail, but it focuses on X-ray feedback of high electric fields very close to a propagating lightning leader. So it's kind of similar to the mechanism I described, but I think it's more focused on the fields from the lightning leader and not so much the background. So people are still trying to sort out exactly how this is all happening and where precisely is the electric field that's doing the accelerating. Is the lightning leader itself a source of the seed electrons, at least partially? Joe Dwyer's mechanism says you just start with one and feedback takes care of everything. If you have a lightning leader, that might be able to inject via X-rays and cold runaway some significant fraction, 10 to the 6 seed particles, and you need less feedback and less amplification. So stay tuned. It's still an active area of research. Okay. Same Tom Warner video. Does anybody need a break? I think I'm sort of on time. Do we need a break? I do not need a break. I'm rolling here. But thanks for asking. Okay. This video again, because I love it, and because it makes so clear that there's a lot happening in the cloud that you can't see. And it sure would be nice to be able to see what the lightning is doing in the cloud. Because that's where lightning initiates. That is a process that is totally not understood very well. Partly because you can't see it. Literally, you just can't see it. It always happens in the cloud. Fast positive breakdown is this process that nobody understands, that is sometimes associated with lightning initiation, where there's some radio source that's moving at about 1/10 the speed of light, which is way faster than it should be over a few hundred meters. I was just talking with colleagues on Friday or Saturday who were dubious of the existence of this phenomenon, fast positive breakdown. I'm pretty sure it exists. A lot of open questions. TGFs, it would be really nice to have a more complete picture than a guess of what the lightning leader is actually doing at the time these gamma rays are being produced. And so we have to see in the thunderstorm to be able to do that. So what would we need to be able to see inside a thunderstorm? Well, we need something that is produced by the lightning that we can detect at a distance and somehow sort out into an image. And it has to be, clouds and air have to be transparent. So optical, no good. Higher energies, X-rays and gamma rays are only made by certain lightning processes, so we wouldn't image the whole thing. But you go down to radio frequencies, and now you're sort of in the game, because lightning emits a lot of radio energy, and below a few gigahertz, you have no trouble getting radio signals through clouds. Above about 10 gigahertz, you start to run into Rayleigh scattering issues and lose too much signal, which is why satellite TV sometimes craps out in heavy thunderstorms. You may not see this in the Netherlands, but in the southeastern US, it's an issue. So, people have been doing radio imaging in astronomy, and there's Nobel Prizes associated with that for decades. And specifically radio interferometry, where if you have multiple sensors on the ground, you can measure time or phase differences of arriving signals and work out with some precision where that thing is in the sky. And so maybe you can make that work to make a radio map of lightning in the sky. For that to work well, you want some frequency range that basically all lightning emits in some form or another. And you also need it to be reasonably high frequencies. HF to UHF are probably the best option. Anybody have a thought on like why lower frequencies challenging? The wavelength is okay. Yep, wavelength. Or you would need very widely separated antennas or detectors in order to measure phase differences over such a long wavelength. And even more fundamentally, antennas are typically wavelength-ish in size. Yeah, but that's expensive. And we may not be able to cobble together, gravitational wave resources to deploy on this problem. So yeah, higher frequency is better because you can get away with smaller antennas and smaller systems. Does anybody know what country? Is it here? I don't know. Could it be here? The Netherlands has the best lightning radio imager in the world? Really? Really? That does seem weird, doesn't it? But it does. You all have the best. It wasn't designed strictly to be a lightning imager. The low frequency array, LOFAR, have you heard of it? Some yes, some no. I was literally on Saturday tromping around this field, the LOFAR SuperTerp. So there's a bunch of these LOFAR stations distributed around northern Netherlands, kind of centered out of Groningen. Been working on that. but there's some of these stations are actually outside the Netherlands entirely. It's this very large network of antennas that's as big as possible to try and for radio astronomy. I don't know if you can. Yeah, you can't see these dots. Well, there's thousands of these antennas distributed around mostly northeastern Netherlands. And they are mostly used for radio astronomy. They're measuring 10 to 90 megahertz all the time. These things, which you can't, so these guys are a bunch of clusters of dots in these images. These guys are an array of higher frequency antennas that are not used for the lightning. But yeah, this is like by far the world's best lightning imager. And it works spectacularly well because they have so many antennas. You know, if you have $100 million, you can do a lot with that. I mean, all of these stations are have dedicated fiber links back to central processing. I mean, the effort that must have gone into creating this thing is astonishing. Why do they what? How do you not have a canal around something in northeastern Netherlands? Everywhere you step is a canal. I think they dug it out in order to elevate and flatten the ground here. Yeah, apparently those, plus or minus 2 centimeters were too much. And I think they also built this up and then intentionally have this canal dug to help drain, to give the water here someplace to go so they don't get too much subsidence. This is what I think, but I'm not entirely sure. I'm not going to show you LOFAR movies. I'm instead going to show you my home movies. There's probably somewhere between 5 and 10 groups in the world who have developed their own lightning interferometers. LOFAR was not the first. Paul Crable and Mike Stock from New Mexico Tech University in the US were probably the first guys to really do this well. And I'm showing you some hardware for version 1.0 of my system. We are now working on version 4.0. So we're doing things much better than this, but in part to show how easy this actually is to do and do reasonably well. I mean, we used terrible antennas, just 2 pizza dishes with an insulator in between, an RF amplifier and filter. The only expensive piece of the system is the digitizer, because you need to capture full waveforms of about 1 second duration, which is about how long a lightning flash lasts, and you need to digitize up at 100 megahertz or more for that 1 second and save all the data. And that kind of digitizing card really wasn't available commercially until like 10 years ago. But suddenly you cross that technology threshold and this becomes pretty easy. Something like this is maybe $5,000. So it's not like cheap, but it's not that expensive. And we deployed 3 of these antennas on 52-meter baselines. And just to give you a sense of what these signals look like, here's that data for one entire lightning flash. So 1 second in that window. So, there's a whole bunch of radio emissions starting right there, which is the start of the lightning flash. Zooming into a millisecond, you see that it's not continuous at all, but is made up of a lot of short pulses. And you zoom in more to 10 microseconds, and it's still these short pulses, which is great because your main goal with an interferometer is measuring time difference between the same pulse measured on 2 different antennas. And the pulsier the signal is, the easier it is to measure those time differences reliably without making a mistake. And the signals are, you can't tell from this giant plot, but if we zoom way in on some individual pulses here, you can see that two antenna signals, they're really pretty much the same, just with a time difference. And zooming in more, so now this is, sorry for the terrible time scale, that's microseconds, so this is 100 nanoseconds. And so those two pulses measured on my two pizza plates are the same, just time shifted. And the way smaller pulses, in fact, actually, let me go back, it's easier to see here. You know, this stuff kind of looks noisy, but in fact, this pulse is this pulse. And this blue pulse here is that red pulse. Like, all these features are, in fact, exactly the same, just time shifted. Yes, question?
Are these data filtered, or this is what you see?
They are, there's a little bit of RFI cleanup that has gone into them.
It doesn't introduce artifacts, I guess.
If you do the filtering well, then no, it doesn't. I'm sort of highlighting this to show how easy it actually is. One key advantage, lightning is a very powerful source. Whereas this is not radio astronomy where we're trying to tease out signals that are 10 times smaller than the galactic background radio emission. Like these signals are big and they don't take a lot to actually capture well. And so what you do is then you take these every pair of antennas that you have and just cross-correlate time windows of that signal to measure the time difference between the signals as a function of time. And you end up with a plot for the entire flash that looks something like this, where every dot is a time window that you ran a cross-correlation on. And this is the time difference between the signal between antenna 1 and antenna 2 in nanoseconds. And if you do that on two perpendicular baselines, it's very easy to then map that to a position in the sky, azimuth and elevation. This is not a 3D, but just 2D. And there's a lot of individual radio sources in here. It's not clear yet that when you put this together into like a map or a movie, how good it's going to be. But it's pretty good, and I've got a bunch of movies to show. So here's a still image of that radio map of the sky during a lightning flash. Color is time. So blue is where things started, and red is where they end over about a second. And so this is the projection where you take the hemisphere of the sky and just drop it straight down onto a circle. So this dotted line is 30 degrees. Sorry, well, the outer, this is the horizon, 30 degrees elevation, 60 degrees elevation. And if you then animate that to get an idea of what that lightning flash looks like in the sky, and almost all these radio sources are actually inside the cloud, so you cannot see them optically. If you slow them down enough, lightning flashes get kind of slow and kind of boring, actually. But you can see what there are, like there's radio emissions from the tips of all of these propagating channels because they're coming from the streamers. It's the streamer time scale of tens of nanoseconds that is producing tens to hundreds of megahertz pulses of radio emission. Oh, right, and now you see these things called dart leaders, where you have fast pulses of radio emission that are traveling backwards down old channels very quickly on the order of 10 to the 7 meters per second. Here, this is not the best movie. Here's another one where I'm not mapping the full sky, but sort of just making a Cartesian projection of the piece where this lightning flash is. This one is a cloud to ground lightning flash. So the initiation here was inside the cloud, and now you've got a bunch of channels coming to ground, kind of like that high-speed video. One of them contacted the ground. From our viewing spot, we have a lot of trees close to the horizon, so we never get clear images down here. Then this lightning flash decides to drop another leader in a totally different location that then starts coming to ground and hits somewhere over here. So all of this, if you saw it visually, it's less than a second. So you just see sort of like flickering. And I think there's yet one more cloud to ground channel. This one's a little unusual. A lot of times lightning likes to send additional strokes down the old channels instead of creating a new one that goes to a different location. This one comes down somewhere over here. Probably like here. And if you remember the high-speed video of just that lightning branching channel coming down, that's like these. But yeah, pretty much all of that is inside the cloud, and all of these sort of dart leaders going around are just the brief flickers of the cloud that you would see this whole thing lighting up, but no ability to see channels. Let's see. That's another CG. Ooh, this is my favorite one. So this is probably our best image. This was not recorded with the pizza plates. We had better antennas for this one. This was version 2.0. But this is a completely in-cloud lightning flash. Like, there are no channels that exit the cloud at all. When you see a lightning flash and just the cloud flickers, but no channels, that's what this is. So there's the initiation, and it moves up through the cloud. That's where a TGF would have been produced. And then it reaches the top of the cloud and starts to go sideways and branches out. This is sort of the bottom end. Lightning has two ends, the negative polarity end and the positive polarity end. In this one, we've color-coded. The negative polarity end is cyan, and the positive polarity end is magenta. You cannot see that in the data. You have to make an informed guess, but it's not that hard to tell the difference. Good, I have it on loop. You see there's sort of a morphological difference. The cyan is very branched, and the magenta is not very branched. And in fact, when the magenta positive leader is first propagating, it is essentially radio quiet. And you can't see it until sometime later it starts flickering after the tip has already passed that point. That feature is called needles and was first reported by the LOFAR guys, and they got that paper into Nature. Nature, the real deal. So anyways, it's amazing to me that effectively 3 pizza plates and 1 fast digitizer and not too much space can make images, time-resolved images that look so good. Yeah? Yes.
But you do not see this in this movie, I think, right?
No, in the previous movies, that's a great point, because optically, by far the brightest part is where it makes contact. And you do not see that pretty much at all in the radio images. And I think the reason for that is the optical emissions you see are proportional to the magnitude of the current in this hot channel, because current equals heating, heating equals optical emissions. But if you're doing radio, you need pulsing in order to be able to see signals from that. And that process, the connection and then the new potential racing up the channel, is like a steady current process, and it just doesn't radiate at VHF. So that's the one thing you can't see very well with something like this. My group, we've gone up to like 1 gigahertz, and it doesn't look very different. And the best understanding is that all of these emissions are really coming from this streamer zone at the tip of a propagating lightning leader, and I'll show something about that. And the very last thing I want to, I'll skip that. Well, this is our most detailed movie of lightning and upward initiation. And you can see some kind of unusual features here when you zoom way in, how these things, yeah, here's the streamer zone, but I'm not sure what this narrow channel is. It could be an artifact of lots of emissions over a wide region that are getting averaged out. I'm going to skip that one. But anyways, the LOFAR guys are totally killing it in this space. They don't get nearly as much lightning as me, for example, but they get these 3D maps that have 10 times more individual points than I do, and like every time they look at a new flash, they find some new process that's happening that nobody has ever reported before. It's very exciting stuff. And so how does this work so well? I think about this sometimes because it's like astonishing how well a really simple system works for this kind of imaging. And it's just, lightning is like the ideal source. High power, very pulsy, and super easy to process. Okay, last thing, that image that I put up in the beginning. There's so much happening as I was preparing this. Like there was the Pasco TGF paper on Friday. This is New York Times 5 days ago. Although I saw this work presented at a conference in Tel Aviv last summer, but it was just published at the end of this year, and for some reason didn't really get picked up by the popular media until like 5 days ago. But I'm glad it did because it's amazing. And so some things you can see here. This, here's the developing conducting channel, and then there's this sort of glow at the tip. That's the active streamer zone. That's where these conducting streamers are being emitted, that sort of then somehow, that nobody completely understands, collapses into a conducting channel and pushes the streamer zone forward. But the question here is, which one is going to attach? I said I would have guessed that one. Let's watch the movie. Let's watch the movie. There we go. No, I was not right. I think these are reflections inside the camera because the connection is so bright. So I was not right. It looked for all the world like it should be one of those, but it was one of these over here. But it's interesting how you can see how even before the descending channels enter the picture, conducting objects on the ground are starting to send up leaders because the electric field between the descending lightning channels and these conducting objects is so high that it initiates and connects upward. That's what always happens in these cloud to ground. It comes down and then something initiates upward. A tree, hopefully not a person, a conducting object, and then the connection is made at some altitude. What's interesting about this one in particular is that So this is the right section of that movie. This one is coming off the lightning protection rod. This one, which is the one that makes connection, is just coming off of a chimney, like the structural building. And then when it makes contact, it causes all kinds of havoc. Have you ever seen a picture of a tree having exploded after being struck by lightning? Because when that happens, if it's powerful enough lightning, it boils the water in the tree very quickly, and the tree just explodes. I assume the same thing happened here. There was either a ton of heating in the concrete, or maybe there's reinforcing bar in there that heated up and exploded. But the takeaway there is kind of lightning goes where it wants to go, and you can try and direct it to where you want it to go, because if it connects with the lightning protection, then the current's all contained in the conductors, and there's standards about how big the conductor has to be so that it doesn't vaporize in a lightning stroke, and as long as you make it big enough, then it's like no big deal. It just goes to ground through copper. The copper is there for the next time it happens. But, you know, even when you have lightning protection reasonably close, sometimes the structure of these channels is such that, like, nope, it really wants to attach there. And there's not much you can do to stop it when it wants to do that. I can't believe there's 3 minutes left and I'm on my last slide. It's a miracle. So, some takeaways. Hopefully you have some appreciation for all the amazing things lightning does, and that like some relatively simple physics can get you at least part of the way towards understanding what it does. You know, you guys are, if you're already physics PhD students, then you know how useful simple scaling arguments can be to like rule in or rule out certain things. That's not a trick you need to know. There's so much old stuff out there that can benefit from a revisit in terms of new technology or new ideas, kind of like that lightning interferometry where 20 years ago, the hardware just wasn't there to do it. People had tried to do it and they got some images, but it just wasn't worth it. But now, for less than $10,000, you can make something that is like world class. And it's kind of astonishing. And lots of examples in there about people being lucky. But every one of those people who was lucky put in the effort in order to be lucky. And just watch, you know? Watch and learn. And with that, I think we're released and free to go. Thanks a lot. Yeah. Question, please. Yeah.
Can you press 2 and then 0 and then enter so that you don't have to press this 50 times? It will go to the 20th.
Oh, slide 20. Sure. Wait, you're saying I can just...
Press 2, then 0, then enter.
How about that? Amazing. I didn't even know you could do that.
I have a question about this structure. Can you actually model this as an equivalent electric circuit with R's and C's?
Yeah. R's and C's, well, yeah.
You have electrolyte between 2 electrodes, you can model that as well.
Sure, I guess you can. I mean, the most important thing would be like the sources. So there are 2 current sources, maybe 3 current sources in the problem. One is the slow current source that's separating these 2. Then what you would have, like, you'd have to like put some electrodes where you want your charge layers, and then there's going to be capacitance between those electrodes. And so how much charge ends up getting deposited in these layers will depend on the current and the capacitance and voltage difference. And then sure, you have this transient current source that is the lightning channel that you turn on at some prescribed point in the system. So, you know, this really is electrostatics, and circuits is also electrostatics, so the answer is definitely yes. Yeah.
Because of the difficulties in imaging thunderclouds or like thunderstorms itself, do we not even have a good estimate on like the volume occupied of the discharges there?
Of the volume occupied by the discharges. So yeah, okay. There's two ways that's guessed. One is with radio imaging techniques like this that can sort of capture the extent of the thunderstorm. The other way people have estimated that is satellite views from above, looking at diffuse optical emissions from whatever the extent of the lightning flash is in the thunderstorm. So even though it's blurry, if you view it from above, where you have a fairly unimpeded view of the top of the thunderstorm, you can see which sections of the cloud are illuminated, and that's a reasonable guess to where the lightning channel is going. So really, as far as I know, the only way to image the channel inside the clouds is with these sort of VHF to UHF radio techniques. Yeah.
So there's this common saying that lightning never strikes the same place twice. Is there any truth to that?
No. Let's see. Using my new trick, get close. Not that one. This one. So here's another cloud to ground flash imaged. Leader starting, thinking about whether it wants to go to ground or not. Maybe it does, maybe it doesn't. We're 200 milliseconds into the flash. Well, wait. Okay, it hit ground here. And it hit ground again. You can't see it. Yep. Yes. Okay. So it does strike the same place twice within one lightning flash when it keeps sending multiple current pulses down the same conducting channel that it already created in the first place. But like in less than a second. So that's when if you ever see a lightning channel to ground that like flickers, it's just actually like hitting the ground 5 or 6 times through the same channel, brightening, dimming, brightening, dimming. Yeah, exactly. But in terms of striking the same place, I mean, it strikes tall towers, the same tall tower all the time. But like, flat Dutch ground with nothing on it, I would say it's very unlikely to strike exactly the same place. Yeah.
The leads themselves, I suspect, already ionized the air. And hence, I was wondering if in the very last bit where it still strands out and finds a connection point in the ground, does lightning also prefer to take one of the other alternative routes that we're still looking at, maybe as multiple strikes at its relatively same speed?
Oh, I see. Like, does it come down first through this one, but then the next time it might come down here and decide to take one of these side branches down? Yeah, that it's almost there, but right, something would have to happen to this channel to make it not want to take the same one, because the same one is ionized all the way back down. Okay, or yeah, the tree is gone. Yeah, that's a good point. It's hard to image the contact points on the ground with that level of detail, but I bet Marcelo Sabo, the Brazilian guy, has probably observed that. So totally could happen. Yeah. Yeah, that is a big open question. Like, what is the charge distribution and therefore electric field distribution in the cloud? Yeah, we don't know that. We would love to know that. I don't know that anyone's figured out a good way to detect that. I mean, you can measure static electric field on the ground and maybe in a distributed array, but that's going to have so much smearing and blurring from whatever complicated charge structure there is when you're at some distance away. It's going to be way more uniform. So no, actually, that's a great question. People still fly balloons into thunderstorms to try and measure electric field vertical profiles, even in just one place. Oh yeah, thank you. But no, we don't know that. So modeling is the only way we sort of get a guess of what's plausible or reasonable. Yeah.
So you said that there's basically like a negative and then a positive end of the flash in the cloud.
Yep.
Is there like any qualitative difference between them? Like is one charge more prone to like hit the ground, or they look different than
yeah. So yes, they are totally different. Their radio emissions are different. The streamer physics at their ends are different. Positive and negative streamers, very different. Because one of them is attracting electrons in, and the other one is pushing electrons out. Negative streamers, big thing that keeps them going is photoionization from UV light being emitted and creating conductivity ahead. Actually, the way negative leaders propagate is this thoroughly bizarre way where seemingly you saw there's the conducting bright channel and then this brush corona at the tip. Negative leaders seem to have this mode where somehow at the end of that corona brush, part of it starts to collapse into a conducting segment that is not attached to this. And then the lightning makes a jump to that conductor that formed ahead of the channel. That's like called a leader step or a lightning step. And the other end just propagates super smoothly. More often than not, it's the negative end that touches the ground, but not always. Yes, both optically and radio, those two different polarities are phenomenologically very different. The positive tends not to branch very much, moves way slower, is way dimmer in radio and optical. The negative has this weird stepping process that keeps it going. It branches more profusely, and it's much brighter optically and much brighter in radio. And I'm not sure we really know why those differences are so stark. I think the streamer guys have to give us some help on that. So simulate 10 to the 8 streamers in a streamer zone. Yeah. Okay. Thanks again. Thanks for your attention. Appreciate it.